So, today we will continue our discussion with the predictor corrector method, which we ended yesterday's discussion. It is important to realize that we are not going to keep on writing down algorithms and doing the proofs to validate that they are correct. We are going to give you a brief conceptual idea of what a predictor corrector method is, and then what a long step path following method is. And then of course, you can go ahead and read more references and the real research papers or books. I have already showed you this particular book, which is very important for your study here, and once this book will have huge material which you can study and enjoy. So, what is a predictor corrector step? I am actually telling it from this particular book, is that you start with you have two neighborhoods here. The first neighborhood is linked to this particular choice of the centering parameter, and this is the N2 0.25, that is theta is equal to 0.25. The next neighborhood where sigma is equal to 1 is associated with the neighborhood 0.5, that is slightly larger neighborhood. So, what is happening is that I have two neighborhoods. So, I start from a point, if I start from a point x naught lambda naught s naught, say in the N2 0.25 neighborhood, what I do is I put sigma 0 is equal to 0, and then I compute grad x naught, grad y naught, grad, that is the Newton steps for the relaxed Newton case with this parameter, the centering parameter equal to 0. So, now what you do, your next x1 s1 s1, x1 y1 s1, how do you compute this? This is x0 y0 s0 plus alpha times, you are doing this line search in the x s y space. Now, observe that you now have to choose, what you do, you choose alpha so large, alpha element of 0 1 large enough so that x1 y1 s1 is in the larger neighborhood. So, you have strayed a bit away from the central path. Now, you must be observing in these definitions, in this drawing, why I am giving a curved from. So, this is my starting point, this is my starting point x naught y naught s naught, basically this is my corresponding point x naught x1 y1 s1, but these are not these are actually not those points. So, this point here corresponds to the point x naught s naught, x, in this particular case it will correspond to the point x naught 1 s naught 1, x naught 2 into s naught 2, maybe I will just write it in a better way. So, here this point is corresponding to x naught y naught s naught in the x y space. So, when I am projecting on the x s space, this point is actually corresponding to, if there are two variables, x naught 1 s naught 1, x naught 2 s naught 2, and then this point which is x1 y1 s1 in the original space is corresponding to x1 s11, x12 s12. Now, you might tell why this is curved, because I am talking about moving along a particular direction from x naught y naught s naught. So, we should go in a straight line, but you have to remember that this space is not the x y space, but the x s space. So, it is a projection of the thing into the x s space, and x1 into s1 by itself is a nonlinear thing. So, here I am tracking the movement of xs, I am not tracking the product xs, I am not tracking the movement in this space, I am not tracking the movement of this vector along the straight line. So, the projection of that gives a curved path in the xs space. So, what I have done this step, what this is called the predictor step. This predictor corrector method actually follows closely in the idea is very close to the predictor corrector method used for solving ordinary differential equations. So, predictor is a predictor part. Now, once I have that x1 s1 s1 y1 s1, I would now compute delta x1 delta y1 delta s1 with sigma k equal to 1. Basically, I will solve star, the star equation, the Newton equation, which you know, which I am not repeating, with sigma k equal to 1. Now, what you do is you do not choose a, so take you sigma equal to 1. So, my centering parameter is strong, it is forcefully taking me towards the central path, the projection of the central path, this is the central path in the xs space. The interesting part is that here I am looking at the central path as a straight line in the xs space when I have just two variables. So, that is much more easier to explain things. So, I will now compute x2 y2 s2, I will take a unit step, my alpha would be equal to 1. And I can actually mathematically prove, which we will not do here because of time constraint, we cannot be so much detailed. This thing, this new x2 y2 s2, that is x2 y2 s2, I can now show that it lies in a smaller neighborhood. So, it is more near the central path. So, I have started from a point near the central path, come down to this and come here. So, I made a much more larger movement than I can do possibly in the case of the short step path following method. Now, you can mathematically prove that if I take a unit step from here to unit step along this direction, I will get a point which will be there. Now, again in this step, when once I am in the smaller neighborhood, I will again choose sigma k equal to sigma 2 equal to 0, and then again I will keep on starting. Here here my sigma k is 1. So, here I have started with sigma 1 equal to 1. Now, I will choose sigma 2 equal to 0 and generate the point x3 y3 s3, and then when that point is in the bigger higher neighborhood, here I have come to x2, here I am in the x2 y2 s2 point, I come to x3 s3 point in the outside, and then I will choose again sigma. You will start by choosing, now from here you will just choose sigma 2 equal to 0 and proceed. You come to this point, choose sigma 3 equal to 1 and proceed. So, in this way back and forth you will try keep on computing. Obviously, at every step you will compute the tau, and the tau will basically you will see it is coming down. So, these are certain things which we will not prove, but now we will go and discuss about the long step path following algorithm. Obviously, it is these things are all can be proved to be following the polynomial time procedure, long step path following algorithm. So, here we will not go into details, but try to explain to you in the long step path following algorithms. I want to explain to you how things what we do here. As we have told before, we use the infinity neighborhood, and just to recall once again, the infinity neighborhood is given as follows, that it consists of all elements of the form x y s in the strict neighborhood, in a strict feasible set, such that xi into si is bigger than gamma times tau, where gamma is a quantity where I is obviously from 1 to n, and gamma is a quantity which is lying between 0 and 1, without 0 and 1, it does not take 0 or does not take the value 0 or 1. So, n minus n infinity gamma is actually, if you look at again the excess space, it is much more easier to look at the excess space, because here I am only talking about the products. So, let me look at x1 s1 and x2 x2, standard 2-dimensional way to describe things. There are hardly in the, once I look into 3 dimension, it will become very difficult for me to describe this thing. So, here again the central path is this. Now, what is the neighborhood in this case? How is it a smaller neighborhood or bigger neighborhood? The answer is yes, it is a bigger neighborhood here. Why? What is this? Xi Si is greater than or equal to gamma into tau. So, if there is a particular tau Xi Si, so suppose if you take x1 s1 x2 s2. So, x1 s1, so which is this value x1 s1, it has to be bigger than something, and x2 s2 has to be also bigger than something. So, basically both of the values have to be bigger than certain amount, certain quantity. So, this neighborhood, so if I put xi si is equal to gamma tau, look, if I look at that line, right. So, every tau is changing, the xi si is taking a different value, gamma into tau. So, x1 s1 is equal to gamma tau, x2 s2 is equal to gamma tau for some tau and some gamma which is fixed. So, you will get a point here and a point here. Gamma is very small, and tau, basically you will get a point here, because gamma is small and whatever be the value of tau, gamma is pulling the tau down. So, x1 s1 is, you will get a point here, corresponding x2 s2 a similar point here. Similarly, you will create points like this, which are actually coming down to 0. So, basically to be more, this is the neighborhood. So, you observe this is a bigger neighborhood, because you take one point here which is x1 s1 equal to gamma tau, you will take the same x2 s2 equal to gamma tau here. So, this is the value of, so this is x1 s1. So, when tau is bigger, this is say gamma tau. So, this will be the value of x1 s1. So, you will take all x1 s1 on the top. So, x1 s1 which is bigger than gamma tau, you will take this part here, this is your gamma tau. So, x2 s2 equal to gamma tau, you take everything which is bigger than x2 s2 equal to gamma tau. So, this is my neighborhood. So, this is my n. So, we start with a point say x0, and we take as much long step as possible, even if it is possible to come to the boundary of this thing. Then take another step here, you can take another step here and come here. So, you can take quite a bit of long steps to come towards the solution. So, what you do in this particular case, how do you take the centering parameter sigma? You basically fix two, you fix two values of sigma, sigma max and sigma mean. So, this sigma max and sigma mean both are in the interval 0 1. Now, at every step k, but you have to remember that sigma max and sigma mean has to follow this inequality. They cannot be, though but sigmas can be chosen from 0 and 1, sigma mean and sigma max has to be bigger than 0 and less than, strictly less than 1. Now, what I will do is that for any k that you choose, for any k, so I am making it slightly more general now in the way I am telling. So, what you do here is that you choose your sigma k is now adaptive, it can change as you change the iteration, it can simply change as you change the iteration. Earlier when we had a short step path following method, sigma k was fixed, it was 0.4 possibly. So, sigma k was fixed, sigma k was sigma for everything. In the predictor corrector method, in one step sigma was 0, other step sigma was 1. Here the corrector step the sigma was predictor step the sigma was 0, corrector step which was the sigma was 1, but here sigma k becomes adaptive. So, this long step path following algorithm takes you more and more closer to algorithms which are more of practical use. One of the most important such algorithm is the Sanjay Mehrotra's predictor corrector algorithm. So, here sigma k is chosen from this set of values. So, you have sigma max, sigma mean and sigma max, and what you do is again using the chosen sigma k find now choose the as much large value you can choose of alpha. So, choose as much large value of alpha in 0 1, so that x k plus 1, y k plus 1, s k plus 1, which is given as x k, y k, s k plus alpha delta x k, delta y k, delta s k, this whole thing is actually in. So, it continues to remain in the neighborhood. So, find the largest alpha for which this value would be this, and that then this particular vector is called x k plus 1, y k plus 1, s k plus 1. So, choose as much large alpha you can, means if you take the 0.1, if you choose a large alpha you can go as much quite far off from the central path actually. But the interesting part is that you are still bounded, you cannot just go towards the boundary where one of the xi's or si's can become 0, which is really not, we cannot do it because xi into si has to be equal to mu and mu plus something. So, it has to xi si both has to be positive. So, we are stopping xi si by this neighborhood which is large, we are stopping xi and si to go to the boundary, any one of them x1 s1 here or x2 s2 here to go to the boundary. It cannot just drop to 0, one of them cannot drop to 0, both of them has to be positive. But giving this large space I am allowing a lot of movement. So, if I can take a lot of movement in much shorter number of steps, I can come towards the solution, and that is the whole idea behind the long step path following methods. Okay. With this we are ending our discussion of the pleasures of linear programming. You see how effectively we can do a lot of things with linear programming, and which is a very important part of convex programming. But these long step path following methods etc. are also applied in convex programming, where my functions are non-linear. So, we are not going to get into those details, but now we are going to study another important class of convex programming problem which arises out of the generalization of linear programming problems, and those are conic programming problems, and a particular part of it which is a special part called semi definite programming problem is something which we are going to concentrate on at this moment. Now, we are coming to a very important class of problems called conic programming problems. In fact, if you give me any linear programming problem, I can always write it as a minimization of a linear function over a convex set. So, in general, every convex programming problem can be posed as a minimization of a linear programming problem over a convex set. So, studies of linear programming problem over convex sets plays an extremely central role in convex optimization. Now, for example, if we take any linear any convex optimization problem minimize f x, x element of C subject to this, where f is convex and C is convex, then one can equivalently pose it as minimize T Now, this problem is a problem where I have two variables x and t, but this function t, this is a linear function in x and t. So, we are basically minimizing any convex this convex programming problem can be viewed as a minimization of a linear function over a convex set. So, this because f is convex, so this is a convex set and C is anyway a convex set. So, in general we want to study minimization of a linear programming problem in where x is in Rn, C is in Rn over some convex set A, because here I have just put C, A is convex. So, this is the class of problems that you will interest us. One of the important problems that we have just finished studying here is the linear programming problem in the standard form, where the set C or A, or in fact I should write here, I should put F instead of confusing things, because here I will use matrix notation and A will come. Now, if you take minimize this x greater than equal to 0, if I can now equivalently write this problem as subject to A x equal to b and x element of Rn plus. If you observe that this convex set is a polyhedral set, because they can be expressed as an intersection of half spaces and hyperplanes. So, a linear programming problem is minimization of a linear function over a polyhedral convex set. Now, how can I generalize this idea? One of the direct generalizations that can come is to write this problem as follows. Because Rn plus is a cone and a polyhedral cone, I can take K to be any closed convex cone which need not be polyhedral. I can take this as a thing which need not be at all polyhedral. One such example is where K is not polyhedral, the second order cone or the Lagrange cone, or I would not get into this Lagrange name and all, or the ice cream cone. So, let me describe this cone K. In Rn it would be of this form. This is less than xn, where xn is greater than equal to 0. So, how do you view it geometrically? If you view it geometrically, let us take the case out of R3. In R3, K would look like the following. root over x1 square plus x2 square is less than equal to x3 with x3 bigger than 0. So, this cone can be drawn as follows. X axis, the y axis, the z axis. This cone looks like this. Not that drawing is not so good, but not very bad either, I would say. If you look at the cone, this looks like an ice cream cone, like the one you get in shops, but this is not polyhedral because the sides are rounded. A polyhedral cone cannot have rounded sides. Polyhedral cones have to have flat sides. I mean, if you want to have a polyhedral cone would be like this, for example. This would be the example of a polyhedral cone. So, this is polyhedral cone, and this is non-polyhedral cone. So, these are the two drawing. So, when I put k is equal to this, so when I have a conic programming problem where I put minimize C transpose x subject to A x equal to b and x is element of k, where k is the second order cone. Then this problem, if I call it conic problem or COP, then COP is called a second order conic programming problem, SOCP, second order conic programming problem. So, I should conic programming problem. So, this is not a linear programming problem in general, but a convex programming problem, because my final feasible set is not polyhedral. So, if my final feasible set is not polyhedral, I cannot call such a problem as a linear programming problem. Today I am not giving examples, but I will soon give you examples of how these classes of problems are important. A lot of important interesting application problems can be modeled as a second order conic programming problem. Now, here we have been concerned essentially with x's in Rn on all this stuff, but Rn is not the only finite dimensional space, though any finite dimensional space can be of dimension n, can be has a bijection with Rn naturally, but it does not mean that I cannot look into any other framework of finite dimension. For example, the set of matrices. We have spoken about semi-definite programming. Now, in this case, basically if we look at finite dimensional spaces from a basis free point of view, then we are essentially talking about any finite dimensional space. So, we are now going to talk about semi-definite programming, and semi-definite programming at this moment one of the hottest areas of convex optimization. One of the hottest area of So, how do you, we have already described a bit about semi-definite programming trying to find its dual. So, let me first today introduce what a semi definite programming problem is, duality etc. will come later on. Now, in our space we will now consider the space Sn is a space of all n cross n symmetric matrices. Now, I will also consider, like if this was Rn, then I have considered the cone Rn plus. So, what is the natural cone here? In this case, the natural cone is the space of all n cross n symmetric and positive semi definite matrices. Now, by A is positive semi definite, which we will now start writing short as PSD, symmetric matrix A. So, if A is element of Sn is PSD, I will just write it in a more clear way. Symmetric n cross n matrix is PSD if and only if x A x is greater than or equal to 0 for all x in Rn. There is also a concept of positive definite. So, A element of Sn is positive definite if x A x is strictly bigger than 0 for all non-zero x in Rn. Now, what I want to tell you is that if you collect all the positive definite matrices, the interior of Sn plus, which we call Sn plus plus. So, this is nothing the set of all PD matrices, positive definite n cross n symmetric PD matrices, positive definite matrices. Now, how do you relate a matrix, say an n, suppose I have a collection of n cross n matrices, suppose Mn just is a collection of space of all n cross n matrices, space of all n cross n matrices. So, how do I say that this space of matrices has an one to one mapping with the space Rn? How do I say Mn is almost like Rn where n has to be decided. Actually, Mn we will soon tell you is isomorphic to n cross n. So, any finite dimensional space is actually related to the Euclidean space of this type. So, how do we do it? So, this is done by something called a Vec operation. So, what is this Vec operation? The Vec function. So, these are some things you have to know about matrices in the beginning to truly appreciate the beauty of semi definite programming. So, let us look at this one. So, what is the Vec operation? Let me just take the 3 cross 3 n cross n matrix, need not be symmetric. A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, if you look at this, my Vec operation, if this is my A, what I do? I take this one, I stack it, take this, put it here as in one column, take the next column, stack it below it, third column, stack it below it. So, that will give me a vector. So, my Vec of A, the vector associated with the matrix A is nothing but A11, A21, A31, A12, A22, A23, A31, A32, A33, transpose, because we write things as column vector. So, at 3 3 3 9. So, this is R 9, which is same as. So, I can write that vec of A is element of R 9. So, vec of A belongs to R 3 cross 3. So, M 3 to which A belongs to is actually M 3 is similar to, if when A belongs to M 3, if and only if vec of A belongs to R 9, R 3 cross 3. So, M of n is isomorphic. This symbolizes in mathematics is isomorphic, means structurally the same, that is there is a bijection between them to R n cross n, where M n is a set of n cross n matrices. Okay. Now, what about S n plus? What about S n? S n also is a space of n cross n matrices. So, is it same as R n cross n? No, there is a little bit of clux, there is a little bit of clutch, small thing that one has to observe, because S n is a symmetric matrix, because A 1 2 is A 2 1, A 1 3 is equal to A 3 1, A 2 3 is equal to A 3 2. So, we have to take those things into account, and once we take these things into account, you will see that S n is isomorphic to the space. How does it happen? Think about it and we will discuss it tomorrow. This would, associated with this is something called an S-vec operation. For example, if you have the S-vec operation, S-vec of A, you do not repeat the vectors, that is the whole thing, you do not repeat the vectors. So, do not repeat the elements here. So, you will see your dimension is getting cut down. So, we will discuss tomorrow what is S-vec A, but now if I am in the space S n, so is there an inner product in S n? In fact, if you take the inner space M n also, I can define an inner product, but for S n the inner product is given as so you to take 2 x and y in S n and the inner product is given as trace of x, actually x transpose y in general, but x transpose is same as x here because it is symmetric. So, x is trace of x y. So, you know the trace is nothing but the sum of the diagonal elements of a matrix. So, now once you have this, then it allows you to frame an optimization problem. Now, I will frame as if I am framing a linear programming problem in the space of matrices. So, I will take an element C from S n and consider minimizing of this is nothing but trace of C x, which is this, subject to so everything is just like R n plus is left with S n plus. A I here what would happen? C is of course in S n, A I is in S n, x is of and B I is, so I will take I from 1 to m. So, the vector each B I is in R. So, the vector B is in R m. So, which is B is nothing but B 1, B 2, B m. Now, this is called a semi-definite programming problem, or more colloquially as SDP. It is very important to note that this problem is not a linear programming problem in the space of matrices. You cannot do a simplex method type of thing and solve this problem. this is in general a convex programming problem, because Sn plus is not polyhedral. The question is why. I will try to explain to you in two different ways. Today, before I end this talk, I will try to just explain to you one simple fact, is that if you take say n equal to 2, a 2 dimensional scenario, that is S2 plus, then what would happen is that S2 plus would consist of all positive semi definite matrices, 2 cross 2 positive semi definite matrices, but my Sn itself is how much, is isomorphic to which space? It is isomorphic to n in R, n into n plus 1 by 2. If I put n equal to 3, it will be 3 into 3 plus 1 by, S n equal to 2, then it will be 2 into 2 plus 1 by 2. So, it will be R 3. So, S2 is actually isomorphic to R 3, is a 3 dimensional space. So, S2 plus, so if you have a symmetric matrix, you will have A, B, B, D, B, C, sorry. So, this is the matrix. So, this is ABC, which is giving you the matrix. So, ABC is in R 3. Now, if you look at it, so what do I mean by this matrix being positive semi definite? It simply means that I should have A bigger than 0, all the principal minors are determinant of the principal minors are greater than or equal to 0, C is greater than or equal to 0, and AC minus B square is greater than or equal to 0. Now, if I look at the whole thing in R 3, is it a polyhedral set in R 3? The answer is no, because polyhedral set is nothing but a set described through linear equations and inequalities. Here I have first two equations inequalities which are linear, but the third inequality is quadratic, it is not linear. So, this set is not polyhedral. So, what you have here is a convex programming problem. So, we have to understand that SDP is a convex programming problem and not a linear programming problem in general. So, if you talk about duality theory and all those things, strong duality always holding for linear programming problem, such things do not happen for conic programming SOCP or this SDP problem. So, in tomorrow's class, I will start discussing the SVEC and give you another very general way of telling why this is not polyhedral. We will show that you can always map this Sn plus to the second order cone, which is not polyhedral. Secondly, tomorrow we will start giving you some interesting examples of problems which can be cast as SDP, because SDP being convex programming problem and there are interior point methods to solve it, SDP is a tractable problem. It is the tractability issue which is the most important thing in optimization. So, we show that a lot of problems come under the category of SDP, and then we will discuss its optimality conditions and duality and a brief outline of how interior point methods can be used to solve it. But that would be possibly the last but one lecture in this course, and the last lecture would possibly take into some more general view of subgradient optimization. So, with this I would end today's lecture. Thank you, and looking forward to talk to you on SDP in the next class, because SDP is a very important part of current modern convex optimization. Thank you very much.